with special relativity introduced, we can define a bunch of invariant properties that we can then use in any particular reference frame in looking at a scattering of one particle to another. And so I want to develop those. And I want to take a look at these particular diagrams. These are kind of like Feynman diagrams, but I don't really mean them to be too accurate. What I want is to have two particles, 1 and 2, scattering, going into another two particles, which I'm going to label 3 and 4. And I'm usually thinking of one particle, P1, going to P3, and that's its momentum. It begins with with momentum 1 and ends with momentum 3. And depending on whether I want to see what's constant over time, like in this direction, or what's constant over space in this direction, I want to do two different things. And so to begin with, having conservation of momentum energy 4-vector in special relativity, we should, momentum is conserved, so we can define the quantity P1 plus P2 as 4 vectors. So P1 plus P2, energy momentum total, that's conserved. And initial P1 and P2 then will be conserved, and it will equal the total at the end, so P3 plus P4, and we can define a scalar by taking these 4 vectors and doing the 4-vector scalar product of them. So we can define S is the variable we call it, and I'm going to use the P1 plus P2 version of that, it's squared. And so that's the total conserved energy squared of the detector. And if we considered these two to come together and make a particle quote there, then this would be equal to the mass squared of that particle. Now, in the second diagram, I'm concentrating on what goes in between the two particles. So if one particle starts with P1 and ends up with P3, and the second one starts with P2 and ends up with P4, then what goes in between is what I want to concentrate on, and I'm going to call that variable t. And here I want to find what changes between P3 and P1, so the difference of those, and that must be then also what's received on the other side, so P2 minus P4. Notice I've switched the sides of those, and I don't really want to keep track of which is which, so I'm going to define another variable t, which is, and now that's a scalar as well, that is P3 minus P1 squared, or P4 minus P2 squared, because the sign doesn't matter. And that is going to be the momentum transferred from one particle to the other in the scattering process. Note that if the incoming particles are identical, or the outgoing particles are identical, we can define another variable u, which just mixes these. And so instead of particle 1 going to 3, we consider it to go to 4 instead, and in which case the momentum transfer works differently, and we have P4 minus P1 squared. Just because perhaps we can't tell P1 and P2 apart, we have to consider the two separately. To show where these scattering invariants come in handy, let's consider the normal scattering case where you are in the lab and you're sending a beam of particles, which I'm going to call P1, is going to be that beam of particles. So they're moving in the lab and they're impinging on a target, which is at rest, which is where the P2 goes in this case. And then from that, you get coming out a P3 and a P4 going in various directions. Often we want to reconsider that case in the center of mass, so we have a shift in frame, a boost to the center of mass frame. The mass of the center of mass frame in this picture is moving with a velocity, which I can represent with this arrow, and if I make that Lorentz transformation, what I have in the end is the center of mass frame where P1 comes in, P2 comes in from the other side, and they scatter and go off in direct angles. And so we should figure out how to actually go from one to the other carefully. So let's actually write down what these four vectors are. So in the lab frame, to begin with, we can write P1, and it's a moving particle with energy E1, and it has a spatial momentum P1, like so. And P2 then is the target, and it is not moving, so its energy is just its mass, and it has no spatial velocity because it's at rest. And so we can already calculate S, however. That's going to be P1 plus P2 squared. And so when we do that, the energy components, the zero components, are going to add and square. So we get E1 plus M2 squared, and we subtract off then the dot product of the momentums, but added, but there's only P1, and so P1 actual dot product, because it's the spatial part with itself, which I'm just going to write as P1 squared. That's the dot product of P1 vector with itself, the magnitude of that vector. Should remember that in this case the E1 there is M1 times the gamma factor for that particle moving, and so that says, contains its velocity, or the way it's often written, M1 over square root of 1 minus V1 squared, and you should remember that's V1 over C1, V1 over C squared. But C is 1 usually for us. And we can also expand that. That's M1 times 1 plus 1 half V squared. So you see it's M plus the kinetic energy. If V is small, we can make that expansion. Now note that the for vector for U1, we had it's moving at some velocity, which we call gamma 1. That's how we find its time component. And then the spatial components are gamma 1 times the velocity vector. So if we want to find this gamma 1 factor, or if we want to find the velocity, we can just divide the spatial components by the time component to find the velocity, or to find the velocity, which is the, we could also call the beta factor. And we can do that with the momentum components too, since there's just a momentum there everywhere. So we can quickly get that V1 in this case is P1 vector magnitude over E1. Relativistically, that's a useful thing to do. I say that all to develop what the center of mass beta factor is. We can quickly write down that this beta center of mass, and I'm going to do the squared version, is just going to be the momentum components added, so P1 plus 0 squared, which is just P1 squared, divided by the total energy squared, which is E1 plus M2 squared. And I'm going to then further calculate what's 1 minus beta Cm squared. And to do that, I'm just going to interpret 1 as the denominator here, the numerator and denominator there. So that's 1. And so I'm going to have E1 plus M2 squared minus P1 squared over E1 plus M2 squared. But comparing the numerator here now with what we defined as S, we see that's identical. And so this is just S over E1 minus M2 squared. We can then find out what the gamma of the center of mass that goes with that. That's just 1 over the square root of 1 minus beta Cm squared. And since we've calculated that all right, we just have to take this fraction, flip it over, and take the square root. And so this is E1 minus plus, sorry, that's a plus there, 2 M2 over the square root of S. And if we look at that, this is the total energy in the lab divided by the total energy in the center of mass. For looking at the conserved quantity T, it's interesting to look at the elastic scattering case, where in the center of mass, the initial energy and the final energy of the scattered particle are the same. That's what it means for elastic scattering in this case. So when we calculate T, in that case, just writing down P3 minus P1 squared, so that's writing that out. That's E3 minus E1 squared minus vector P3, spatial vector, minus P1 squared. But of course, since E1 and E3 are the same, we can cancel out this part. And then do the multiplication. And so when we do the vector multiplication of the P3 minus P1 squared, we get minus P1 squared plus P3 squared minus 2 P1 dot P3. And since the magnitude of P1 and P3 are the same, and we can do the dot product, and that's the momentum of the particle in the center of mass. That's 2 times P center of mass squared. That's either P1 squared or P2 squared, P3 squared. And then times 1 minus cosine of the angle between P1 and P3 in the center of mass squared. So note, again, we can say that this is, call this minus q squared, the momentum transferred. Oh, I should say, this is minus because the momentum is the vector, the form momentum of the transfer is a spatial-like vector, therefore its magnitude is less than 0. So here in the center of mass frame, we're connecting a magnitude of momentum transferred to the angle. And so we can then write that dq squared, is 2 times the momentum in the center of mass squared times sine theta cm d theta cm, taking the derivative of this line here. And if we further combine that, we can relate the d theta cm to a solid angle and say that this is equal to momentum in the center of mass squared d omega over pi. We've integrated over 2 pi to do that. And we can connect that back now to a Rutherford scattering. In that case, the mass connected with P1 is much less than the mass at P2, and V1 is much less than 1, much less than the speed of light. And so rather than writing as we had before, d sigma d omega was z e squared over 4 pi epsilon naught. Kinetic energy, all of that squared over 1 over sine to the 4th theta over 2. We can write instead something like, how does the cross-section vary with q squared, which is very similar, and it's 1 over 16 pi v squared z squared over 8 pi epsilon naught. Oh, excuse me, this is a 16 over here, not a 4. And then 1 over q squared here. Q to the 4th, excuse me. What this actually says is that the cross-section for larger q squareds goes down, and that larger q squareds are less likely at that 4th power of q as they go.